Okay.
So here's the question, right? Let me get you with me, please. So a rectangle initially has dimensions 3 by 7. All sides begin increasing in length at a rate of 4 centimeters per second. At what rate is the area of the rectangle increasing after 18 seconds? Okay, so we need to, let's probably get a picture, right? I mean, not that the picture's going to be so earth-shattering here, but our picture, there's our rectangle. So what are our variables going to be here then?
X and Y.
Okay, X and Y. And so what would I probably call the long dimension here? Call it the,
X.
okay, but I mean, I could, but I could even, I mean, I could, that's fine. I could do that. Okay, we'll do it your way. There's another way we could do it too. We'll call that X and we'll call that Y.
This is how usual data do it in math.
Okay, yeah, okay, that's fine. I mean, we can do it that way. The other thing we could do is we could do like X plus 7 and X plus 3 if we wanted to. I mean, either way, this will be fine. So then what are our snapshot values? X equals 7, Y equals 3, okay. And what about this part right here? Both X dot and Y dot, right? So we could say X dot equals Y dot equals 4, right? What are we trying to find? A dot, okay? Except, is that true, that we wrote there? Is that the snapshot we're looking at? Yeah. The snapshot isn't at time 0. When's the snapshot? It's at 18, isn't it? Right? That's the snapshot we're interested in. So that's really not 7 and that's not 3. Right? You see my point? Okay, so what is the value after 18 seconds?
Would you?
I mean, we could write an equation down if we wanted to, but we could probably just finesse our way through this. So if both of these dimensions are increasing at a rate of 4 centimeters per second,
So that.
after 18 seconds, how much have they both increased by?
7.
Yeah, 4 times 18 should be 72, right? So then the length is not really 7, it's 7 plus 72, isn't it? Okay, so it's actually 79. And this is just going to be, what, 75?
Yeah.
Okay, that's probably where there's a mistake, if there was a mistake on this. Okay. Does that make sense? Okay. And so we're trying to find, you said we're trying to find A dot, right? Okay. So then what's our parent equation going to be? A equals XY, there you go. Okay. And if I differentiate implicitly, what am I going to get? So this is product, right? Right, so I've got to do product rule, so I've got to do the first times the derivative of the second plus the second times the derivative of the first. And the derivatives are with respect to t, so they're going to be dots. Okay, and we know all that stuff, don't we? Right? So A dot then is equal to 79 times 4 plus 75 times 4, which is the same thing as 4 times 79 plus 75, which is just 154. And so that's just going to give us, what, 616 for our answer? What would the units be? Yeah, and we're measuring lengths in centimeters and times in seconds. So we have to have units of area over units of time, because it's dA dt, right?
Yeah.
Okay, does that make sense? So, I mean, to me, that's the tricky part right there, isn't it?
Yeah.
Okay. And how can you clarify that, though, in your mind as to why, not just to solve this problem, but to kind of see that coming in the future also? Remember that the snapshot, not all problems are like this, but if it's kind of a physics type problem like this, where it's giving you a specific time and you've got to make some calculations. Didn't we do one like this earlier with like a kinematic situation? I think we threw something up in the air, or so I can't remember what it was. But then that's both a blessing and a curse. It's a curse because you have to do a little bit of extra work, but it's telling you specifically that's the frame in the video that you're interested in. It's the one where t equals 18. Okay? So you got to find all the quantities at that particular time, which might require some additional work sometimes. Okay? Okay, I got one more I want to do with you that just is so cool. There's one in the problem in the book that I really like. Thought there was a problem. Let's see.
This because he was
Maybe I'm imagining.
Oh, you're
something.
not fancy? Yeah. I seen that like once earlier. And he's saying that's not. What? Let's go to like, where does it snow a lot?
You know, I remember, speaking of Meacham, I remember hearing once that, I don't know if this is true or not, it seemed like it was a reliable source. It is the town in the US, in the lower 48, that is most likely to have a white Christmas of any town over a certain population. I mean, if it's like more than 5
Well, we
people.
have 79.
Meacham was the town.
Yeah, well,
It is questionable.
Yeah.
Dude, I can't even do two questions.
we've multiple times been the coldest place in the nation, including Alaska.
That seems wrong because everyone's comparing the statistics. I remember
No.
it's at the coldest place in Alaska, I think.
No. At that time,
Like,
not holding the record, but at that time.
you know,
We were the
like,
coldest
today,
place.
sucks. I can't, yeah, I'm pretty sure it's,
Yes,
it's like
But
freezing,
it's
very cold.
probably close to today, but
not today. The coldest,
It's not
negative
about
4
what connection, it's probably colder.
degree.
degrees.
That's the only
Kelvin.
place. Did all the roads in
Oh
Wyoming are
my.
good? You know, we look up the definition of a place. Place. Jeff, hey, you should go look at I don't know where it's at. South of Pilot Rock, go down.
It's the whole world.
You have to follow Highway 395 go down south.
You have, where's
This is
Yeah,
from-
he said it is. Yeah.
That's the airport.
Where are you trying to get to?
Airport? Where do you, it's international water, it's like, it's the coldest.
I would have one.
Well, that's not what he said, but that's what he said. Well, it says you. Why don't we just get a big pool and
Oh, yeah.
I think the one I think I'm.
Yeah. We have a road.
Okay, how about this one? This is a very cool problem. Now, I wrote it down a little differently than it shows up in the book, because I want us to think our way through some of the stuff that they gave me.
Or is it different?
So click and close for a second and just focus on this. This is, I really think this is interesting. You should too. As a spherical raindrop falls, as a raindrop falls through the air, it can be approximated as a sphere. It's pretty close. It's not actually, it's an oblate spheroid because there's a little bit of force. The air resistance is going to flatten out the side that's falling very slightly. But the surface tension of water is really big, and if it's a pretty small raindrop, it's pretty darn close to a sphere. So we could approximate this as a sphere, and it works just fine. When it reaches a layer of dry air, it begins evaporating when it hits that dry air. Okay, I want see if we can reason out here and show that we would expect the radius of the raindrop to decrease at a constant rate. Now, first of all, what's that mean? The radius of the raindrop is decreasing at a constant rate. Okay, so the radius, the radius is decreasing linear, right? So after 10 seconds, it will have decreased by a certain amount. After 20 seconds, it will have decreased by twice that much. Okay? Now, that's not at all obvious though, right? Because as the radius of the raindrop decreases, the volume is changing at a different rate, right? We know that in order to go, for example, in order for a sphere to go from a volume of, but let's say the radius is 101 centimeters of this sphere. Changing from 101 centimeters to 100 centimeters is a drastically different change in volume than we'd see if we went from 2 centimeter radius to 1 centimeter radius, right? Everybody agree that there's a lot more volume stored in that shell between 100 and 101 centimeters than there is between 1 and 2 centimeters, right? Everybody agree?
Yeah.
So that's not at all obvious that that should be the case. Okay, but it is. How come? Can we show why? Now here's the first question I've got for you. If a raindrop is falling through dry air, where is the water, when it's evaporating, it's losing volume, correct? Okay, so where physically on the raindrop does it lose the volume? From the outside, from the surface, right? It's not losing volume from the center of the raindrop, it's only losing volume from the part of the raindrop that's exposed directly to the air. Agreed? Okay, so how can we make a mathematical statement that captures that idea? Think what we just said there. The evaporation is only occurring from the surface of the raindrop, right? So evaporation is kind of an English word that, to the math gods, is a rate of change of what quantity? No. The evaporation. We're physically losing water, volume, right? We're losing, the volume of water is decreasing. Okay, incidentally, the surface area is going to change too, but that's really not what we're talking about. If we're extracting water, water is a three-dimensional substance, right? We're changing the volume of the raindrop. So we would say that V dot it's only happening from the surface, so it's got to be proportional to the surface area, doesn't it? Right, if I double the surface area, wouldn't it make sense that I'm going to double the rate of evaporation then? Because there's twice as much surface exposed to the air?
Yes.
Okay? So that's how we say that mathematically, right? If S stands for surface area. What's that symbol?
Fish.
Kind of. That's a proportionality symbol in math. That's literally in math, that's saying V dot is proportional to S. Okay? We can't do algebra with proportionality symbols. We can only do algebra with equations or inequalities, but in this case, an equation. So how do we write that as an equation? If I say that x is proportional, or y is proportional to x, how do I write that as an equation? What if I graph a line that demonstrates proportionality? I want you guys to come up with this. I don't want to tell you. So if we graph a line that demonstrates proportionality, where's the line? Has to go through what point?
There.
Has to go through the origin, doesn't it? Right? To demonstrate, that's direct variation. You called that in Algebra 2, you would have called that direct variation, right? So you have this line going through the origin. That's direct proportionality. Well, if I want to predict y based on the value of x, what's the equation of that line? mx, right? And then b is 0, isn't it?
Yeah.
Okay, so it's mx, but instead of m, we're going to call it a k this time.
Okay.
Okay, and we can call it m, it's fine. In fact, let's call it m for a second. Well, I think maybe that's, just randomly calling it k might seem weird. So what if m is 1/2? If m is 1/2, then that means that y is always going to be half as big as x, but if x doubles, so does y, right? If x triples, so does y. Agreed?
Yeah.
If m is equal to 10, then y is always going to be 10 times as big as x, but they still grow proportionally, or shrink proportionally. Agreed? So really, that describes the characteristics of the proportionality, but it doesn't matter what m is. Regardless of what the slope is, it's a proportional relationship. right? So you gotta have this constant in there. And typically, we don't call it an M. We call it an M in this context because we're talking about a line. But typically, we give it the title K for the constant of proportionality. So if we want to write this as an equation, we would just say that V equals Ks, where K is some positive constant. Okay, it's just, does that make sense? We don't know what it is. It's gonna depend on the situation. But at this point, we don't know what K is, but we do know that we should expect to see this proportionality. So we should expect this equation to be true for some value of K. Agreed?
Yeah.
Okay? Okay, so okay. All right, so let's see if we could come up with a parent equation here that we could use and differentiate implicitly. So what are the quantities being compared here? I mean, we're looking at V and S, but the quantity that's being differentiated this time is a V, isn't it? Right? So what if we started off with just the volume equation? V equals 4/3 pi r cubed. That's the value that's being differentiated, right? Okay, what if I differentiate implicitly with respect to t? What am I going to get on the left side? V dot. What am I going to get on the right side? 4/3 pi times 3, which would be 4 pi r squared, r dot, right? Okay, 4 pi r squared, does that seem familiar?
Yes, sure.
What is that the equation of?
Is that surface?
That's surface area. That's surface area of a sphere. How about that? So
Someone came up with that.
V dot is equal to S r dot, right? Does that make sense?
Area.
Yeah.
That
Right.
makes sense.
Sure.
And so then if, now, you know, something didn't seem right to me when I said this. So in this case, because V is decreasing, what's the sign of K gonna be?
Negative.
It's gonna be negative, isn't it? Right? Does that make sense? So we gotta make one little change here. Because we're actually losing volume this time, right? We're evaporating, we're losing volume, and so K should be a constant that's less than 0. Okay? Okay? So now, well, look at this. We independently came up with these two equations defining V dot. So by substitution, doesn't it make sense that Ks must equal S r dot?
Uh-huh.
Yeah.
Okay, so if we set those equal to each other, we could divide each side by S, and look what we get. K equals R dot, where we define K as being some negative constant. So what's that telling us? That R dot is equal to some negative constant. Isn't that what we want to prove? Right? We just showed that the radius of the raindrop is decreasing at a constant rate. Okay, probably a better way to show this would have been, this seems a little clumsy, because usually you would define K as a positive, but if I did that, so if I'm going to make one little change here, I want you to see how this impacts it. If I said K is greater than 0, then I would just would have put a negative sign there. Right? And it would have looked like this. R dot equals negative K, where K is some positive constant. Right? So we're just showing that it's decreasing at a constant rate. That just proved it. Right? Okay. Pretty good. We got a little bit of time. How much time, when are we out of here? So we could even take like related rates. So you ever watch those, like probably at some point you've watched like a science fiction movie where ants like get real big or something, right?
Yeah.
So the ants, they get huge and they dominate the earth. I mean, even something like King Kong, where you scale up a gorilla. Okay, we can do a really quick related rates analysis that shows that it is impossible for any of that stuff to ever happen. Like King Kong could not exist. Okay. Couldn't exist.
That's evolution.
Okay, but if you look at animals that got scaled up, like you have to go back and look at dinosaurs, right? Or in modern day, I mean, on a much smaller scale, look at elephants or something like that. But in particular, if you look at dinosaurs, because dinosaurs were extremely massive, right? Their physiology was nothing like what you see when you scale up an animal. Let's think about why this is. Like if we took a gorilla, for example, and we were going to scale it up, I don't know, how many times bigger is King Kong than a regular gorilla, like 10 times or something. So if you scaled it up by, if you scaled something up by a factor of 10, now, so you gotta understand a little bit of engineering here, right? A little bit of biophysics. So for any material, like if you take wood or bone or anything like that, the supporting, I don't want to say this, the structural integrity of the material is proportional to its cross-sectional area. Okay? So if I take a post or something, and if I want to support twice as much weight, I need to increase the cross-sectional area of the post by a factor of 2. Stands to reason. Okay. All right. So then, if you scale up a gorilla, by a factor of 10, and you were to take a cross section of the supporting bones, like the femur in that gorilla, what you're going to see is if the height of the gorilla is increasing by a factor of 10, what do you suppose that's going to do to the cross-sectional area of the bone? It's going to increase it by 100, right? Think of it in terms of like a square instead of a circle, right? Let's say the bones had square cross-sections. If I'm going to uniformly scale up all of the dimensions by a factor of 10, that square is going to get 10 times wider and 10 times taller, right? Everybody agree? And you can think about it in terms of the dimensionality. If I'm scaling something up by a factor of 10, that means the linear dimensions are increasing by a factor of 10. That would mean that all of the captured areas would have to increase by a factor of 10 squared, because we're scaling up everything in all 3 dimensions uniformly, right? It's going to be an exact replica. It's going to be a dilated version of the gorilla, right? Okay, but so that would mean that the weight-bearing capability of the gorilla's femurs would increase by a factor of 100. That sounds pretty good. But what's happening to the volume of the gorilla if we scale it up by a factor of 10? It's cubic. So the volume of the gorilla is increasing by a factor of 1,000. Now, what's going to be important? What's going to be the most important quantity when we're talking about the total mass or weight of the gorilla? The height, the area, or the volume? The volume, right? It's the volume of stuff in the gorilla, matter in the gorilla, that creates its mass and therefore its weight. And so the weight of the gorilla, or the mass, is going to increase by a factor of 1,000, but its ability to bear weight of the weight-bearing bones is only going to increase by 100. And so what's the inevitable consequence of that? Can't stand up, can't support its own weight. If it takes a step, the forces involved with doing anything would shatter the bones, right? And so what do you notice about, like, if you look at, next time you see a picture of a dinosaur, look at the physiology of the dinosaur. Like if you look at a T-Rex, for example, where's most of the weight in the T-Rex? Well, I mean, yeah, there's a long tail, but most of it's in the legs. If you look, the legs are hugely disproportionately large on a T-Rex, way out of proportion, right? How come? Because it's a heavy animal, so to be able to move around, to be able to move around, it didn't use its arms very much, did it? To be able to move around, it has to have those big weight-bearing bones. You'd see the same thing with an elephant. You'd see the same thing with any really big animal. It's gonna have to devote a lot more tissue to supporting weight, which is why it's not really, in our universe, on our planet Earth, it's not really a good evolutionary plan to have really, really large animals, because they have to consume all that extra food to do what? Just to support themselves, to be able to grow very large legs to support themselves, and that's not efficient, right? And so only in really extreme circumstances where there's hugely abundant food supply would that ever happen. Like it wouldn't happen period. Right. You don't see any of those enormous animals. That was only at that one period, in one epoch where there was just all this massive, there was greenhouse gases everywhere, and things were growing like crazy, and there was all this ready food supply available, but now you wouldn't see that. I don't know, just kind of interesting little related race example, how you can kind of, I hate to ruin all those movies for you, but ants could never do that. Well, okay, yeah, but what's gonna happen, so the ants have these little chitinous legs, right? You're right, but why are ants so amazingly strong? Because they're so tiny, right? They're so like, they can lift huge, multiples of their body weight, but that's because they're on a very, very small scale, where they don't have to have much of a support base to lift that weight, because their volume is really small, right? It's that whole concept of, if you shrink a sphere down, right, the ratio of volume to surface area, you're gonna get, I want to say this, think about those little spindly antlers. If you were to scale this thing up by a factor of, like those ants are scaled up by a factor of, like, just say it's like 1,000 or something, right? If you scale those things up by 1,000, then that means you're gonna have the weight of the ant is gonna increase by 1,000 cubed, which is a trillion, right? Whereas the ability of the ant to support itself only increases by 1,000,000. And so at some point, those legs are just gonna shear off, right? And ants can have those tiny legs because they're on such a small scale. If they weren't, we couldn't do that because we're on a bigger scale, right? It all has to do with the relative scale of the animal. Okay. Like fleas can jump how many thousands of body length? It's crazy. Yeah, but we can't do that because of the scale we're on.
You're talking about
That's why he has a suit. It supports all the ways. It's part of it. It's just the suit.